Hey everyone, I hope you're doing well. In this video, I'm going to be talking about absolute value inequalities. While you can find the timestamps here, they're also linked in the description. If you don't have a solid handle on absolute value equations, I suggest you watch one of my earlier videos on that topic first. When you see the word inequalities in math, you should be thinking about the less than, greater than, less than or equal to, or greater than or equal to symbols. Let's start by looking at an absolute value inequality that uses a less than symbol. This 5 represents the distance from 0. This less than symbol means that we have to be less than 5 units away from 0. And this is our expression that has to be less than 5 units away from 0. So we know that if x is equal to negative 5, we would be 5 away from 0, and if x is equal to positive 5, we would also be 5 away from 0. Since the distance has to be less than 5 units, x can't actually equal negative 5 or positive 5. However, it could equal something like negative 4.99, or something on the higher end like positive 4.99. While x could technically get closer to negative 5 and positive 5, I hope the negative 4.99 and positive 4.99 give you the idea. Any number that is to the right or greater than negative 4.99, but to the left or less than 4.99 is going to make this inequality true. Here we can say that all the numbers that are greater than negative 5, but less than positive 5 are going to make this true. When we have a less than or less than equal to inequality, we can then write this as a compound inequality of negative 5 is less than x is less than positive 5. This represents all the possible values of x that make this absolute value inequality true. To graph this on a number line, we'll put an open circle on this negative 5 and an open circle on this positive 5. Since x has to be greater than negative 5 but less than positive 5, this represents all the possible solutions that make this inequality true. Keep in mind that there are infinitely many solutions for x that make this inequality true. Also, pay attention to these open circles. When we have open circles, it means that x can't actually be the boundaries. If we fill in the circles or they're solid, it means that we have a less than or equal to or greater than or equal to symbol. Now let's look at an example that has a greater than or equal to symbol. This 3 tells us our distance from 0. And its greater than or equal to symbol tells us that we have to be 3 or more units away from 0. Now it's our job to find out what values of y will be 3 or more units away from 0. We should already know that if y was equal to negative 3 or y was equal to positive 3, we would be 3 units away from 0. Since we have a greater than or equal to inequality, these values for y are acceptable. Now we have to ask ourselves what values of y will also be 3 or more units away from 0. Numbers like negative 3.1 or 3.2 or 3.3 would be more than 3 units away from 0. And numbers like positive 3.1 or positive 3.2 or positive 3.3 are also going to be more than 3 units away from 0. It looks like numbers to the left of negative 3 or smaller than negative 3 are going to make this true. And numbers to the right of positive 3 or greater than positive 3 are going to make it true. Here we can say that y has to be less than or equal to negative 3. And we can say that y has to be greater than or equal to positive 3. Since either one of these inequalities makes this true, we can say that y is less than or equal to negative 3, or we can say y could be greater than or equal to positive 3. As long as y fits into one of these categories, we're going to make this absolute value inequality true. To graph this, we'll put a closed circle on negative 3 since y is allowed to equal negative 3, and we'll draw an arrow to the left. And since y is allowed to equal 3 or greater, we're going to put a closed circle on positive 3 and draw an arrow to the right to represent all the numbers greater. Pay attention to these filled in circles as they let us know that these actual values or these boundaries are allowed to equal our variable. A key pattern you want to recognize with these types of problems is that when you see a less than or equal to symbol, you're going to end up with a compound or an and inequality. And when you see a greater than or equal to inequality, you'll have an or solution. Now that we've gone over some background, let's try some examples together. In the rest of this video, I'm going to go over 6 different problems. While the first 5 examples are just solving these absolute value inequalities, the 6th one will be an application word problem. Let's start with example 1. First, it's good for us that this 2x minus 7 in the absolute value is by itself. Since this is a less than symbol, we know we're going to have an and compound inequality. This 2x minus 7 has to be less than 1 unit away from 0. For that to happen, it has to be greater than negative 1. Numbers that are greater than negative 1 are numbers like negative 0.9, negative 0.8, negative 0.7, and those are all less than 1 unit away from 0. To be less than 1 unit away from 0 on the positive side, this 2x minus 7 has to be less than positive 1. To solve the equation on the left, we're going to start by adding 7 to both sides. From that, we'll get 2x is greater than positive 6. And dividing both sides by positive 2, we're going to get x is greater than positive 3. To solve the equation on the right, we'll also start off by adding 7 to both sides. From that, we'll get 2x is less than positive 8. And dividing both sides by positive 2, we're going to get x is less than positive 4. The values of x that make this absolute value inequality true must be greater than 3, but less than 4. Any of the decimals or fractions in between 3 and 4 make this true. Since x can't equal 3 or 4, we're going to have to put open circles on 3 and 4 on the graph and connect them. Let's try example 2 here. Right away, we should be glad again that this absolute value is isolated. And notice how since we have a greater than or equal to symbol, we're going to have an or inequality. Since we have to be 7 or more units away from 0, we can say that 4c plus 5 has to be less than or equal to negative 7. Hopefully this makes sense because numbers that are less than or equal to negative 7 are numbers like negative 8, negative 9, negative 10, and they're all more than 7 units away from 0. On the positive side of the number line, we can say 4c plus 5 is going to be greater than or equal to positive 7. We say greater than or equal to positive 7 because numbers like 7, 8, 9, 10, and 11 are all numbers that are 7 or more units away from 0. To solve our inequality on the left, let's start by subtracting 5 from both sides. We're going to get 4c is less than or equal to negative 12. Dividing both sides by 4 here, we'll find that c is less than or equal to negative 3. To solve our right inequality, we're also going to start by subtracting 5 from both sides. We're going to get 4c is greater than or equal to positive 2. And dividing both sides by 4, we get that c is greater than or equal to positive 1/2. The values that are going to work have to be less than or equal to negative 3, or they can be greater than or equal to positive 1/2. These represent all the possible values of c that make our absolute value inequality true. To graph this, we would put a solid or filled in circle at negative 3 and draw an arrow to the left to show all the numbers that are less than or equal to it. And we would also put a filled in or solid circle at positive 1/2 and draw an arrow to the right, or all the numbers greater than it. This would represent the graph of all the possible solutions. Let's try example 3. Right from the start, we notice that we have to get this isolated. We have to get rid of this negative 3, and it looks like we're going to have an and inequality. To isolate our absolute value, we're going to have to divide both sides by negative 3. The negative 3's on the left are going to cancel out, and we're going to have the absolute value of 2 minus 5 over 4m is greater than or equal to positive 6. Remember that whenever we multiply or divide an inequality by a negative value, we always flip the inequality symbol. While initially it looked like we had an and inequality, we actually have an or inequality. Keep an eye out for these types of problems because it gets a little tricky when you multiply or divide by negative values. Now that our absolute value is isolated, we can write our two separate inequalities. Since we have to be at least 6 units away from 0, on the negative side of the number line, we can say that 2 minus 5 over 4m is less than or equal to negative 6. And to be greater than or equal to 6 units away on the positive side of the number line, we can say that 2 minus 5 over 4m is greater than or equal to positive 6. To start solving on the left, we're going to subtract 2 from both sides. We're left with negative 5 over 4m is less than or equal to negative 8. And we can multiply both sides by negative 4/5 to cancel out the negative 5/4. Since we're multiplying by a negative value, we're going to switch our inequality symbol to a greater than or equal to, and we'll have positive 32/5. As a mixed number, we can say m is greater than or equal to 6 2/5. On the right here, we're also going to start off by subtracting 2 on both sides. We'll have negative 5/4 m is greater than or equal to 4. And multiplying both sides by negative 4/5, these are all going to cross cancel, and we're going to be left with m, and we're going to flip the inequality symbol to a less than or equal to, and we'll have negative 16/5. As a mixed number, we can say m is less than or equal to negative 3 1/5. This represents all the possible values of m that make our inequality true. On a graph, we'll put a solid circle on negative 3 1/5 and draw an arrow pointing to the left, or numbers that are smaller than it. And we'll put a solid circle on 6 2/5 and draw an arrow to the right to point to numbers that are greater than it. This would be a graph of all the possible solutions. Let's try example 4. Right away, let's try to get this thing alone. To do that, we'll have to get rid of this positive 3. And from the start, we should be thinking that this is an and inequality. To isolate the absolute value, we're going to subtract both sides by 3. And we'll get the absolute value of 4x minus 5 is less than positive 6. Since we have to be less than 6 units away from 0 on the negative side, we're going to say negative 4x minus 5 is greater than negative 6. On the positive side of the number line, we're going to say negative 4x minus 5 is less than positive 6. To start solving on the left, we're going to add 5 to both sides. We'll get negative 4x is greater than negative 1. And we'll divide both sides by negative 4. And that'll flip our inequality so we get x is less than positive 1/4. Solving on the right, we're going to start by adding 5 to both sides. We'll get negative 4x is less than positive 11. And dividing both sides by negative 4, and we'll flip the inequality to get x is greater than negative 2 3/4. This would be our final solution. To graph this, we'd put an open circle at negative 2 3/4, as well as an open circle on positive 1/4. Since the values between these numbers work, we're going to connect them here. Excluding negative 2 3/4 and positive 1/4, all the numbers in between them make our inequality true. Let's try example 5. First, we need to get this thing alone. And to do that, we'll have to get rid of this 2/7 and negative 2. And from the beginning, it looks like we're going to have an OR inequality. To isolate the absolute value, we're going to start by adding 2 to both sides. We'll have 2/7 multiplied by the absolute value of 4y plus 6 is greater than or equal to 12. Multiplying both sides by 7/2, these 2's and 7's are going to cross cancel, and we'll be left with the absolute value of 4y plus 6 is greater than or equal to 42. This 2 and 12 cross cancel to make 1 and 6 times 7 is 42. Now that we've isolated our absolute value, we can now write our two separate inequalities. First, we can write that 4y plus 6 is less than or equal to negative 42. Then we can write 4y plus 6 is greater than or equal to positive 42. To start solving on the left, we're going to subtract 6 on both sides. We'll get 4y is less than or equal to negative 48. And we'll divide both sides by positive 4 to get y is less than or equal to negative 12. To solve on the right, we'll start off by subtracting 6 on both sides. And we'll get 4y is greater than or equal to 36. And dividing both sides by positive 4, we'll get y is greater than or equal to positive 9. This represents all our possible solutions. Looking at a graph, we'll put a solid circle here on negative 12 and draw an arrow pointing to the left. And we'll also put a solid circle here at positive 9 and draw an arrow pointing to the right. This graph is a visual representation of all our possible solutions. And that brings us to example 6, our application word problem. Pause the video to read the question to yourself, then unpause it when you're ready to go over it together. Since we need to know the mean price or the average price, we're going to have to add up the 10 different prices of the laptops and then divide that by 10. The sum of all the prices is $6,640. We're going to divide that by 10. The average price of a laptop is going to be $664. To represent this problem using an absolute value inequality, I set up a verbal model here. The price of any laptop, which is going to be X here, minus the mean price of $664, has to be less than or equal to $50 away from our average price. This less than or equal to symbol lets us know that we're dealing with an AND inequality. Since this absolute value is isolated, we can write our two separate inequalities. We have X minus $664 is greater than or equal to negative 50. And we have X minus 664 is less than or equal to positive 50. To solve the inequality on the left, we're going to add 664 to both sides. And we find out the price of a laptop has to be less than or equal to $714. To solve the inequality on the right, we're going to also add 664 to both sides. And we find out that the price of a laptop has to be greater than or equal to $614 to fit in the range. As a compound inequality, we can say $614 is the least amount the laptop can cost, and $714 is going to be the most. This is our compound inequality solution. Out of the 10 different laptops, only 4 of them fit this criteria: this 650, this 670, the 660, and the 650. We can conclude that 4 of the laptops fit this condition. And that wraps up this video. If you found this helpful, please let me know in the comment section below or by giving this video a like. Keep up the good work, and I'll see you in the next one.